we are Team Nexus, and today we present our project, an AI-powered PLC code generator. The goal of this system is to translate plain English instruction into IEC 61131 PLC code, making industrial programming faster, easier, and more reliable. Problem statement. PLC programming today is a slow and error-prone process. Engineers must write structured text or ladder logic line by line, which takes a lot of time and depends heavily on skilled experts. Our solution automates this process. The system accepts natural language as input, generates PLC code, validates it, and allows engineer to visualize it in both structured text and ladder diagram. This is not only saves time but also reduces error and dependency on highly specified manpower. Architecture. Our architecture is designed for both accuracy and performance. Initially, a direct LLM approach struggled with inconsistency and irrelevant outputs. To optimize this, we introduced a Retrieval-Augmented Generation system. Here, how it works. User queries are converted into embeddings using sentence transformer. These embeddings are matched against stored IEC compliant templates in ChromaDB language model, ensuring that the generated code is both syntactically correct and domain aware. We further optimized performance by separating the database layer with PostgreSQL, which not only stores generation history but also manages vector embedding for fastest retrieval. We reduced the complexity of queries, making interactive and more effective. Combining FastAPI, RAG, and modular database, we created a pipeline that is faster, more accurate, and scalable compared to a naive single LLM design. On the front end, we optimized usability. We used React.js for fast and component-based architecture and Tailwind CSS for responsive design. This optimization makes the system for more practical for engineers because they can not only see the generated code but also verify the logic through a visual before deployment. Here how it's work. In our input section, we have a two choice whether it's a structured text or a ladder diagram. We have to give a description so that the model can perform the generated code. For example, structured text program for four-way traffic light system with north, south, east and west signals. The timer for green is 10 seconds and yellow is 3 seconds. Here, how our code generates. The generated output will be displayed on a output section. This is our output. We can copy the output and we can use for a further applications.
Another optimization, we focused on validation. Instead of stopping at code generation, we tested everything in CODESYS simulation. This allows us to confirm logic accuracy with needing physical hardware. For example, in a traffic light controller case study, our system generated PLC code from plain English and the simulation ran successfully validating the logic and safety constraints. In the real-time industrial use case, problem statement in the stamping process, paths are the transfer to end-of-line conveyor for visual or automatic inspection, after which they are placed into a specific container. Here is the output of an ST. The optimized architecture delivers strong results. Deployment time reduced by 70%, commissioning error drops by 50%, training efficiency improved with new engineering learning 65% faster compared to traditional method. These results prove that our architecture is not only a technical sound but also a practical conclusion. To conclude, our project demonstrates an optimized AI architecture that combines large language model, retrieval systems, and interactive visualization for PLC programming. By focusing on accuracy validation and usability, we create a system that can transform how industrial automation projects are developed. Our team contribution. Balachandra Sriram in model development, Chandresh in process validation, Ram Kumar in logic realization, Navina in UI design. Thank you.